Hello, dear students. In this lesson, I'm going to explain AC circuit and transformer. I got many requests from the students to solve section 3 in chapter 6. Okay, so in this section, we have some topics. The first topic here is the effective current or the RMS current. Okay, but before starting explaining about the effective current and the effective value of potential difference and current, I would like to tell you some information about the types of the current. Okay, so the types of current, we have three different types of current. Okay, types of current, we have three different types of current. The first type is direct current. And the second one, direct current, DC. Okay, DC battery, DC or battery. The second one, it is DC pulsating current. And the third one is AC current from the generator. Okay, we have three different types of current: DC of battery, and the DC pulsating current of generator, and the AC current. In DC battery, according to its name, in DC battery, the direction of the current does not change. Look, okay? The direction and the magnitude of the current does not change. In which of the following currents the direction and the magnitude of the current does not change? In DC battery only. In DC battery, the direction of the current is steady, directed, and its direction does not change. Neither the direction nor the magnitude doesn't change. Okay. The second type of the current is DC pulsating current. So, as you learn it in DC generator, the components of the DC generator, the permanent magnetism, the conducting loop with the commutator and the two brushes. So this commutator can be used to converting AC current to DC pulsating current. So by using many loops and many commutator, we can achieve a little pulsating current. So how can you reduce this pulsating of the current? By using many loops and many commutator. Okay. In DC pulsating current, like DC generator, the direction of the current doesn't change. Okay, but if you look, as you can see in this figure, this is the magnitude of the current. Okay, per unit of time. So if you look, the magnitude of the current changes. Why? Because at this point, the magnitude of the current is 0. Okay, the current increases until it reaches the peak. Okay, at this point, the current is maximum. I am maximum current. Then the current drops until it reaches 0. So what is the magnitude of the current at this point? I is 0. Then increases until it reaches the maximum point. So what is the type of this current? Is the DC pulsating current. Okay, it's like a pulse. Okay, so by using many commutator and many loops, we can achieve a little pulse, a steady directed current with a little pulse. Okay, by using what? Many loops. In that case, by using many loops and many commutators. Okay, so the third example of current is AC current. In AC current, the magnitude and direction of the current changes. Both magnitude and direction changes. Okay, so what is this? This is current. Okay, per unit of time. So in this figure, this is the magnitude of the current and the potential difference changes continuously. It is magnitude and direction changes. At this position, the current is positive. Current here is positive. Okay, and here is negative. Okay, this is negative. So the magnitude also changes. The magnitude also changes. Why? Because the magnitude of the current has zero value at this point. So then the magnitude of the current increases. It depends on the orientation of the coil. Okay, like according to this equation, and AB omega sine omega t. So the magnitude of the induced EMF or the current depends on what? The angular displacement. Okay, it depends on the angle of the orientation of the coil. At this point, current has maximum value. At this point, current is zero. This point between maximum and zero. So here, the direction of the current is positive, but here is direction of the negative. So it means that the conclusion of this explaining, we can get that in which of the following, the magnet and direction of the current changes. In AC current or DC pulsating or DC battery? In AC current. In which of the following, the magnet of the current changes, but its direction does not change? In DC pulsating current. In which of the following, neither the magnetic nor direction doesn't change? In directed DC current, like, or the DC of battery. DC of what? DC of battery. Okay. This is about the types of the current. What is the RMS value or RMS current or effective current or effective value of potential difference or current? The effective current, and sometimes we call it RMS current, root mean square current. RMS current, the value of alternating current. So it means that the effective value is the value of alternating current or DC current. Absolutely is a value of alternating current. Okay? The value of alternating current that gives what? Gives the same heating. Same what? Same heating. Same heating of what? Same heating effect that corresponding value of directed current. Does during what? During the same time. Okay, so it means that which one has more power dissipation? 10 ampere effective, 10 effective current, or 10 ampere of effective current, or 10 ampere of maximum current in DC? 10 effective current of AC or 10 ampere of maximum current in DC? They have the same. Why? Because according to this definition, the RMS current or effective current is the value of alternating current that gives the same heating of DC current. Okay, so look at this. What is the type of this current? This is AC current. What is this? This is AC current. Okay, in AC current or AC current, AC current has what? AC current has the maximum values. Has what? Maximum value. Okay. What is this? This is maximum value of current or potential difference, IM or VM. And also, what is this? This is IM or VM. Okay, this is the maximum value. And also here, IM, VM. So it means that the AC current has maximum values of potential difference or current. Okay, it has maximum value of current or maximum value of potential difference. Maximum value of potential difference and maximum value of current. The second magnitude of the AC current has instantaneous current. Has what? Has instantaneous current. What are these dots? This is the instantaneous current. Okay, what are these dots? Instantaneous current. So what do you mean by instantaneous value of current or potential difference? It means that it is magnitude at each instant. Okay, so it changes and it depends on what? It depends on the orientation of the circuit. So how can you finding the instantaneous value of current or potential difference? V instant is equal to what? is equal to Vm sine omega t, the angle of the loop. So, is it possible for the instantaneous current has the same magnitude of maximum current? Yes. When does V instantaneous is equal to Vm? When angle is equal to 90 between the plane of the loop and the magnetic field. Because as you know, the orientation of the coil is very important to change the magnitude of the instantaneous value. Okay, so it means that the orange dots are represent for what? These dots represent for the instantaneous value. Okay, what are these? This is I instant or V instant. Okay, so it means that we have V instant and instantaneous current. Okay. Another value of AC current is what? Is the effective current. Is what? The effective current. The magnitude of the effective current is less than the magnitude of the maximum current. Okay? This is, what is this? This is I effective, or this is V effective. So it means that the effective value of current or effective value of potential difference is the magnitude of AC current or DC current of AC current. That gives the same heating of what? Of DC current. Okay? So it means that in AC circuit, in AC current, also we have maximum value of the current and maximum value of potential difference. Okay? So this is all examples about the all values of the AC current. Look, as you can see in this figure, in AC current we have three different values: the maximum value, the effective value, and the instantaneous value. How can you find the instantaneous value of potential difference and current? By using this equation. Okay, so this equation is based from the Faraday's equation for the generator. Okay. The electrical energy converted to internal energy at some point in a time in a resistor is proportional to the square of the instantaneous current, because power is equal to I square over R, does not depending on the direction, as in the question 3 section review. Okay, so we have a question here. Look, why the energy produced by alternating current with a maximum value is not the same as that the produced by the directed current? The answer is, so which one has, this question is like that. Which one has more power dissipation? The 10 ampere of 10 ampere maximum of AC current or 10 ampere of maximum of DC current? Absolutely the 10 ampere of DC current. Why? Because this 10 ampere, the maximum value of 10 ampere of directed current is always 10 ampere, never decreases, it never changes. Okay, but in AC, the AC, when we say maximum current is equal to 10 ampere, this 10 ampere only at the peak is 10 ampere, not at the other points. The answer is the energies are different. Why? Because during a cycle, the alternating current is at its maximum value only for what? An instant. However, the DC current is the largest at all instants. Okay? Only at the peak, the current has maximum value. At the other points, is less than the maximum value. But for the directed current, is always has maximum value. So we can conclude that in DC current, we have only what? Only maximum values. Maximum value. So DC has only the maximum value of current and potential difference. Look, for example, if you have two circuits, okay, DC circuit, DC current, okay, DC circuit and AC circuit, okay, so both are connecting with the resistance, with the bulb, for example. Look, for example, this is AC, this is DC, this side is DC. Okay, for example, this is a DC of battery, okay, positive, negative. And when connected with a light bulb, okay, so after the switching on, we can see that the light is glows, okay. And for example, assume that the maximum current of this DC source is, for example, 10 ampere, okay. What is the magnitude of the current? The maximum value of the current. DC has only maximum value. The DC current has not effective and the instantaneous. In DC current, only we have what? We have the maximum values, okay. Maximum current is equal to what? 10 ampere, okay, 10 ampere. And assume that the resistance is equal to 5 ohm. This is assumed, okay. For example, just resistance is equal to what? 5 ohm, okay. What will be the power dissipation here? P lost. P lost is equal to what? So in that case, we can calculate the power dissipation or power loss. But before finding the power loss, I would like to draw the circuit for the AC also. Okay? For example, if we have an AC source, okay, connected with the light bulb, okay, so here the current is flows, but the maximum value of AC is also 10 ampere. What is the type of the source? AC source or AC current. the maximum value of AC source is also 10 ampere. Okay, and for example, they have the same resistance. Same what? Same resistance, 5 ohm. What will be the magnitude of the power P loss or power dissipation here? Or by another way, in which examples, we have two examples here, in which examples more power dissipate in the resistor? More power will lose through the resistor. We have to calculate, okay? So both maximum current, they have the same value, okay? But I know the power in DC has more power dissipation than the power in AC. To calculate power dissipation in DC source is equal to what? Im squared R. Im squared R, okay? Replace DC, P loss in DC is equal to what? 10 squared times 5 is equal to what? 10 squared 100 times 5 is equal to 500 watt will be lost or will be lost, or 500 watt is lost in the DC source. But in AC source, to find the power dissipation or P loss in AC, P loss in AC is equal to what? You have to use the effective value of the current. You have to use what? The effective value of current. IE squared times R. Okay? So IE is equal to what? P loss in AC. IE is equal to Im over radical 2 square times R. Okay? So in that case, Im is equal to, replace, Im is equal to 10 divided by radical 2 square times resistance. You can calculate, and the result is less than 500. Okay, the result should be smaller than 500, 300 or something like that. I don't know. We have to calculate. I'm gonna bring my calculator. By calculator, you can calculate that Im 10 divided by radical of 2 is equal to something, square is equal to 50 times 5 is equal to 250. 250. And also you can calculate here because power in AC is half of its power in DC. Okay, times 5 is equal to 250 watts. So which one is bigger? Absolutely, the 500 watt is bigger. So it means that power in AC is power in DC is bigger than power in AC. By which factor? By factor of 2. Power in DC is twice as much of the power in AC. Okay, power in AC. Okay, so and you can say power in AC is half of power in DC. So which one has more power dissipation? AC or DC? Absolutely DC. Why? Because in DC, the magnitude of the current does not change. It's always 10 ampere, for example. But in AC, the magnitude of the maximum value is at its maximum only at one instant, only at the peak. So we can prove that. We can prove this equation. I effective is equal to what? IM over radical 2. Okay. So how can you prove this equation? According to this equation. Okay. So as you know, power in DC is equal to what? Power in DC is equal to IM squared R is equal to 2 times power in AC, I effective squared times R. Okay, so R with R cancel. What does remain? IM squared is equal to 2 times IE squared. If you rearrange this equation, IE squared is equal to what? IM squared divided by what? Divided by 2. IM squared. Times square root to remove this square. Okay. Finally, we got radical times square cancel. What does remain? Only the effective value. Radical times IM square. This square cancel with the radical, and radical 2 is radical of 2. So we proved that the effective value of the current is equal to what? IM over radical 2. I effective is equal to what? IM over radical 2. You can say I effective is equal to 1 over radical 2 of IM. Okay. IE also you can write 0.707 IM. IE approximately equal to, not exactly the same. Approximately is equal to 2 over 3, a little bit more than 2 over 3 IM. Look, the effective value of the AC current is a little bit bigger than 2 over 3 of maximum the current. And also you can write IE 70%. 70% of maximum value. So these are the value of the effective current. Maybe they will bring in the exam like that. Which of the following is correct about the effective value of the current? IE is equal to 1 over radical 2 IM. This is correct. IE is equal to 0.707 IM. Yeah, also this is correct. IE is equal to 2 over 3 IM. Yes. IE is equal to 70% of IM. Yes. Okay, be careful. So for you can rearrange the equation also. IE is equal to IM over radical 2. IM is equal to what? IE times radical 2. Okay. So also you can write for the potential difference. If IE is equal to IM over radical 2, VE is equal to what? VM over radical 2. VM is equal to what? VE radical of 2. And also you can write VE is equal to 0.707 VM, VE is equal to 70% of VM, VE is equal to 2 over 3 of maximum value of potential difference. Okay? Look. Look, the I effective RMS current is called, or the effective current, the same thing. The RMS current, what do you mean by RMS current? It means that I effective or effective current is a little more than two-thirds of what? I maximum. Because 2/3 is not equal to 0.7, is equal to 0.6. So that is why IE is a little more than 2/3 of IM. And also you can represent and you can rearrange the equation of the effective current and the maximum current. Okay? So another note here. So this note is very important. Be careful. When the alternating current are generated. When what? The alternating current are generated. Look, what is this? This is the alternating current. Okay? This is alternating current. Look. When alternating current are generated, each of the maximum potential difference, maximum current, effective potential difference, effective current, frequency, and the angular speed or angular frequency remain unchanged, constant. Look, so this is the value of maximum values. Okay, the maximum value does not change. Vm and Im does not change; it's constant at the P. Okay. And the effective value also does not change. What is this? This is the effective value. The effective value of current and effective value of potential difference remain unchanged. The frequency of the current does not change. The angular speed does not change. Okay? But what is changes during the alternating current? The instantaneous value of potential difference and the current changes. Okay? The instantaneous value of what? Of potential difference and the current changes. What are the? This is the instantaneous value. Instantaneous value of what? Of the current and potential difference. Look, the maximum value of the current here, for example, 10 ampere. Here also 10 ampere. Here 10 ampere. 10 ampere. Does not change. Okay? The magnitude of the effective current does not change. It's still constant. But the magnitude of the instantaneous changes during the alternating current. Why? Because at this point, the magnitude of the current, 0. At this point, current, 5 ampere. At this point, 10 ampere. At this point, 0 ampere. So that is why the instantaneous value of potential difference and currents are changes. Okay? In the exam, maybe they will bring like that. Which of the following changes during the alternating current? Which of the following changes? The RMS value of the potential difference and current? No, does not change. The maximum value does not change. The angular speed does not change. Frequency does not change. Instantaneous value of potential difference and current? Yes. Okay? Only the instantaneous value of the current and potential difference are changes during the alternating current. So that is all for today. Hope you enjoy and get the benefits from my lesson. Thank you very much. Thanks for listening.